Let's do some more analysis of graphs of exponential functions. So notice what I have here. I have the basic exponential function 2 to the x in blue. And then I have 3 to the x in red. Notice how it rises quicker because the base is bigger. And then I have 5 to the x in black. Now on the left it's harder to see, but none of them should really be touching the x-axis because they don't have any x-intercepts, and there's actually an asymptote across the x-axis. Remember, there's a horizontal asymptote. So this is a border. And notice to the y values, for 2 to the x, they keep getting bigger and bigger. The same thing happens for 3 to the x, but at a much quicker pace. So when x is 3, I'm at 8 for the 2 to the x function, but I'm already at 27 for the red function, and I'm already at 125 for the black function, which is rising much quicker. So since the bases are bigger than 1, they're increasing functions and getting bigger and bigger quicker. The bigger the base, the quicker it rises. Now let's look at the next case where I have these bases that are less than 1. So a half to the x, a third to the x, a fifth to the x. In other words, 0.5, 0.333, and then 0.2. They keep getting smaller and smaller. The bases are less than 1. And notice what happens. They're decreasing functions. The blue function is the half to the x, and then the red function is the 1/3 to the x, and then the black function is the 1/5 to the x. And again, the x-axis is an asymptote, horizontal asymptote, and it's really a border. And notice what happens, like when x is 5, the blue function is 0.03 approximately. The red function is even smaller, 0.004, and the black function in scientific notation, it's 0.00032 because it's giving me, remember, e to the -4. That's a number in scientific notation, so it's even smaller. So they're decreasing and decreasing quicker and quicker. Now let's look at this one function, f of x equals 2 to the x minus 1. Now that takes the basic function 2 to the x, which we had right here in blue. It takes 2 to the x and shifts it 1 down, like the parabolas that we looked at that would get shifted down. The minus 1 takes all the y values and shifts them down, and now the horizontal asymptote is no longer the x-axis, but the line y equals -1. So everything has to stay above this border y equals -1 because they all got shifted down by 1 unit. So you may have that happen where your graph shifts up or down. Notice in the next one, so that would be y equals -1 for your horizontal asymptote. In the next graph I have the basic function 1/3 to the x, so that's really a decay, a decreasing, but then there's a +4 that happens next to it, and that really shifts the graph up 4 units. So I no longer have my horizontal asymptote being the x-axis, but I have the line y equals 4 as my horizontal asymptote, because what happened was my basic decreasing 1/3 to the x function got lifted up 4 units. So these are just some things to keep in mind. Base less than 1 is a decay, plus or minus a number shifts it up or down, and along with it, so does the border or the asymptote. Let's look at some application. We looked at the exponential function c(a) to the x, where c was the initial amount and then a was the growth or decay factor. Bigger than 1 growth, smaller than 1 decay. Now we can look at this exponential function's base in more detail. So this base a could be composed of this 1 plus r term, where r is really a % growth given to you or a % drop given to you based on how the problem reads. Let's look at an example. It says a bacteria population starts with 400 bacteria and doubles every hour. Give a model or equation for the number of bacteria n after t hours. So since it's doubling, this tells us that it's going to be an exponential growth. And doubling means you keep multiplying by 2. So the growth factor a is 2 because your bacteria keep doubling. So if I'm looking at f of x equals c a to the x, I already know the growth factor to be 2 because the bacteria keep doubling. And I also know how many bacteria we started off with. We started with 400, so my model is going to be f of x equals 400, 2 to the x, but since I'm supposed to use n and t, let's adjust those. N of t is going to be equal to 400 times 2 to the t. So this is the equation that describes how many bacteria there are after t hours. For example, after 2 hours, I would plug in a 2 and so forth. Let's say if I want after 5 hours, we will have n of 5, plug it into the model, 2 to the 5th, do order of operations correctly, raise the 2 to the 5th first, get a 32, and then multiply it out, and you get 12,800 bacteria. Let's look at this example. A population of bacteria starts with 400 and increases by 20% every hour. Come up with a model for n, the number of bacteria after t hours. So this is a little bit different because here they already told me the growth factor. They told me that it doubles. But in the current example, I have to look at the problem this way. There's actually a percent growth. So I have my 100% bacteria, which is denoted as 1. Then they increase by r%. So I have to add a percentage to 1 to get my growth factor. So in this case, since r is 20%, r is going to be 0.2 and a is going to be simply 1 plus r because I'm increasing my number of bacteria. So 1 plus 0.2 gives me 1.2, which is really the growth factor in this problem. This is my a. It doesn't double, it doesn't increase as quickly. As the hours go by, I only get a 20% gain on the original 100% bacteria I had. Whereas here, on the original 100% bacteria I had, I gain another 100%, and that's why the base, or the a, ends up being 2, because they're doubling, they're growing by 100%. Here they're only growing by 20%. So my model very similarly is n of t. I start with 400 bacteria, that's my c, and then my growth factor is 1.2 because of the 20% growth raised to the t. So compared to the above model, those bacteria grow much quicker than this one because they double and these only increase by 20%. Okay, so now we have a population of mosquitoes that start with 400 again, and they get sprayed some chemicals, so only 3/4 of them remain each day. So as the days go by, only 3/4 of them are left. In other words, I have the bacteria, or the mosquitoes, they keep decreasing. I have 400 on initially, they start with, then only 3/4 of them remain the next day, and only 3/4 of those remain the next day, which means my decay factor, remember, because this is less than 1, so I have a decay happening. My decay factor in this case is actually already given to me to be 3/4. So I have a population P of t that's going to start with some amount and go a to the t as its decay factor. So P of t, initially I started with 400 bacteria. The decay factor is already given to me, the 3/4 raised to the t. So each day that goes by, I only have 3/4 of the previous amount left, therefore multiplying each time successively by powers of 3/4. So if they ask me how much is left after 10 days, I could just plug in a 10, for example. So after 10 days, if I plug in 10 for my t, I'll raise 3/4 to the 10 first on my calculator for order of operations. I get some decimal, I carry some digits, multiplied by 400, and I have approximately 23 mosquitoes left after 10 days. Okay, a population of mosquitoes again starts with 400, and they get sprayed with some chemical, and 35% dies off each day. Now this is a little different than before when they said 3/4 is left each remaining day. That means 75% was left each remaining day, so 25% of it went away. But they automatically gave you the growth factor, which was the A that we plugged in. This is going to be one of those cases where they're giving me the R to be 35%, or R equals 0.35 in decimal form, and this is the loss each day. So this time, since there's a loss, I do 1 minus R. R was given to me, and 65% of mosquitoes still remain as the days go by. So I have P of T. I started with 400 mosquitoes, and I still have, as the days go by, 65% of them left, raised to the T. So this is going to be a decay, because as the days go by, I keep losing the mosquitoes. 35% go away, and 65% still remains. Whereas here, 25% or a quarter was going away, and I still had the 75% remaining. So they die off quicker in the second case. And graphically too, if you just want to have a visual going, this is going to be a decay. And I'm starting with 400 mosquitoes, and over time they're dying off and going lower and lower. I put $2,000 in an account paying 5% annual interest compounded annually. This means at the end of every year you get interest. What is the amount in the account after 5 years? This is compounded annually, and the interest is given to us in annual terms. So we're going to use A equals the amount we started with, 2,000, 1 plus, there's a growth, 5%, so my R is 0.05, raised to the T, the years that go by. So since it was compounded annually, I just added the interest per year, raised it to the 5th power because it was a growth by 5%, did the calculation of that first, and that spit out 2,552.56 cents is what you'll have in the account after 5 years, meaning you made 552.56 in interest. Now if the problem is worded compounded semi-annually or quarterly or monthly, you may use this other formula, which is a little bit different than this one that just says annually, where n is equal to 1 time only. Semi-annually would mean n is equal to 2, so twice a year you get interest. Quarterly, n is equal to 4 times a year you get interest. Monthly would be 12, and so forth. So it would be this formula where the variables are defined as the amount of money, the principal you invested, R is of course the interest rate, and you'll have N, which is the thing to pay attention to in the word problem. So let's look at the slightly different example. I invest $2,000 in an account paying 5% interest per year, compounded quarterly. That's the key word that tells me N is equal to 4. How much money do I have in the account after 5 years? So all I have to do is go plug in the appropriate information. So 2,000 is my principal, 1 plus my interest rate is 0.05. Quarterly means 4 times a year, N is equal to 4, and then NT, 4 times T. I'm going to get a model, and then I'm going to go plug in the 5 years for T. So I did the division, now we're going to combine once I get the base raised to the 14, now I know it's 5 years later, so I plug in T for time. So we raise it to the 16, 4 times 4 is 16. We apply the exponent to this base first. We carry some digits from our calculator, multiply it by 2,000, or following order of operations. So we get 24.39 cents. In other words, 5 years later, that's how much that's sitting in. Oh, actually we plugged in the wrong T. We should go back and plug in T equals 5. Sorry, because it's 5 years later. Okay, fixing that mistake. 5 years later, T is 5, so we raise it 4 times 5 to the 20th power, apply that exponent, and then we get this, carry it from your calculator, so ultimately we have 25.6407 cents sitting in the account 5 years later. So we made an interest of $564.07 cents, which was a little bit more than if it was just annually. And that's about it.